This is video 29.2. We will be studying alpha decay. The question: a uranium atom decays to a thorium atom by the emission of an alpha particle. We'd like to know, what is the energy released by the decay? And what is the kinetic energy of the alpha particle after decay? These are the masses of the uranium and thorium atoms in terms of the atomic mass unit. And we'd also like to know, what fraction of the total energy released does the alpha particle take away in kinetic energy? Step 1 will be to find the mass lost in the decay. After that, we can convert it to an energy and go from there. We have the mass of an alpha particle in atomic mass units. And because after the decay there's just a thorium atom and an alpha particle, it means that the final mass after the decay is the sum of these masses and has this value. Now the mass lost is equal to the initial mass of the uranium atom minus the final mass, which consists of the alpha particle and the thorium atom, and has this value in atomic mass units. Now we can find the energy released. It is a fact that one atomic mass unit is equal to 931.5 MeV. I'm just stating it here, but it's derived essentially using E equals mc squared, where you could convert U into kilograms if you wanted, multiply it by c squared, and then convert to electron volts, and you would have this value. But this is a convenient equality to remember. So we know the mass lost in atomic mass units. We know how much energy that a single atomic mass unit corresponds to. So we can find the energy released in mega electron volts, where mega, once again, is 10 to the 6. This is how it would normally be stated, but for the rest of the problem, we'll also want to know the value in joules. So we multiply by the conversion factor, and we obtain the energy released in joules. Now let's find the kinetic energy of the alpha particle. For this, we'll use conservation of momentum. Suppose the uranium atom is initially at rest. After it decays, the alpha particle and the thorium atom will shoot off because that energy released is turned into kinetic energy. But they'll shoot off in such a way that momentum is conserved. Because we started out with zero momentum, we have to end up with zero total momentum. And they're in opposite directions. So this implies that the momentum of the alpha particle after decay is equal to the momentum of the thorium atom after decay. Now the total energy after decay consists of the kinetic energy of the two byproducts of the decay, the alpha and the thorium. But we just said that P of thorium is equal to P alpha, so we can plug that in to the right side where we did have P thorium. I've replaced it by P alpha. And now notice I can factor out the P alpha squared. Now, in order to continue, we'll need to make sure that everything is in a consistent system of units. So I'm going to convert the masses into kilograms. This is the mass of one atomic mass unit in kilograms. And then do the same thing for the thorium atom. Now, look at the boxed equation. We know all of the terms inside of the parentheses. And we would like to know P of alpha, because once we know P of alpha squared, we can find the kinetic energy of the alpha particle, because the kinetic energy of the alpha particle is simply P alpha squared over 2m alpha. And m alpha we know. So we'll plug in what we know into the parentheses, and we know the left-hand side because that's the total energy which we just found. Continuing, if we simplify that term which was in parentheses, we have the following value. And as stated, we want to solve for P alpha squared, which has this value. Now, the kinetic energy of the alpha particle is simply equal to its momentum squared over twice its mass. And now we know each of these quantities, and we can plug them in, and we obtain the result for the alpha particle. Now let's find the fraction of the energy which the alpha particle takes away. The rest of the energy going into kinetic energy of the thorium atom. So we just take the ratio, and we find that it's 0.98 or 98% of the total energy is carried away by the alpha particle. And that concludes video 29.2. Check out PhysicsX on the app stores. This revolutionary physics app for smartphones and tablets contains over 100 videos and 500 multiple choice questions designed by education experts. It's been proven to improve scores for intro college physics, AP physics, MCAT physics, and more. Just look for the blue icon.